My name is Alba, and as Esperanza explained a bit, I'm going to explain the final results of my project, which consists of the development of a toolbox that is mainly created with Jupyter Notebooks to compare atmospheric composition datasets from different sources. As you can see already in this slide, the main sources that the main datasets that I have been using are the CAMS model, Tropomi sensor, EASI sensor, and GOME2 sensor from NetOp. Next slide, please. So, just to give a bit of an introduction about me, it's going to be short. I come from Spain, and I studied my bachelor's degree in the University of Lleida. It was in mechanical engineering, and during the last semester and the last year actually also, I spent some time studying and working in South Korea. And I later came back to Europe, and I started studying a master's degree in geospatial technologies, which is an Erasmus Mundus program. And I'm currently officially studying at Nova University of Lisbon, where I'm writing my thesis actually about this project. But I've also started to work in Switzerland as a software developer intern at a company that is called Meteoromatics, which works with meteorological data. I have been doing this project for this program with the support of my mentors, which were Antti Ines from ECMWF, Federico Fierli from UMETSAT, and Michael Rasinger, also from ECMWF, which I actually want to thank a lot because their support was really, really important for the development of this project. Next slide, please. So, just to start a bit with the motivation of this project, basically the idea came from ECMWF, and they had three main objectives behind this development. First of all, they wanted to validate different data sets. So it was very important to know if some data sets from some satellites were accurate when comparing them to CAMS model, which was developed by ECMWF. Once these data sets are considered valid, which is something that is going to happen after this project, well, they will check. I mean, the idea of ECMWF is that they can have more coverage of data, and then finally, once everything is implemented, the idea is that it's possible to detect anomalies and problems in the data sets when comparing them against each other. And so, well, these are the main motivations, but actually there is a problem behind the whole comparison, which is that it's not trivial since the metadata is not similar at all between data sets, and these data sets are usually stored in different formats and also in different they actually have different resolutions, as I will explain in the next slide. So these are the sources that I have been using for this project. So we have CAMS model from ECMWF, and I actually used the forecast dataset, and I also used the monthly means dataset. And so I got the following atmospheric components that you can see on the third column. And we can see that the data for CAMS is always gridded, and it's actually not so heavy compared to the sensor data. Continuing with the other datasets, we have data from Tropomi sensor, which is non-gridded, and it's usually daily. We can see here the file size, which is 60 megabytes, and that only corresponds to a part of the track of the satellite, which would be in Europe. So actually this Tropomi is actually very, very, it consumes a lot of resources of the computer when trying to handle this data, and this makes the comparison against CAMS very slow. Then we have GOME2 and EASI data. These both sensors have gridded data, and they give information about monthly means. And they also have non-gridded data, which is also more complicated to handle. We can see already on the right also that the file formats are always different, and they can range from GRIP to NetCDF to HD5P. We also see in the columns in the middle that the horizontal resolution is also not common in any of the sources, and yeah, that would be it. Now, currently, this toolbox that I created can compare CAMS forecast against Tropomi and GOME and gridded data, and also CAMS monthly means against GOME and EASI monthly data sets. Next slide, please. So to explain a bit more about the code structure, we have this basic structure. So we have a folder, which is data, which basically the code uses this folder to store all the data sets, because it's possible to download them and so on within the Jupyter Notebooks. Then we have a folder called functions, where we can find all the functions that are related to general issues, such as the match of the data, the units conversion, and the plot visualization. And then we also have 5 more files that have only the functions that refer to each data set. So we have functions CAMS, functions GOME, functions EASI, and functions Tropomi. Finally, we have these examples, which I called main. And basically here we can see how to combine the different functions to get all our final results for each of the possible comparisons that we can make. Next slide, please. Here, I wanted to show a bit of the workflow. So once we get into one of the main files, we are going to run all these following instructions, let's say. So the user can should first install the software, obviously, and then he will be able to run the imports and also the related functions. Then the user can define a component, an atmospheric component, the sensor name and the model, which is always CAMS for now. And then the program itself is going to tell the user if this comparison is possible or not. Since we have that sometimes there are some atmospheric components that are not available from some sources. So it's important to check this before we move on, because it's not going to be possible to download the data. Once this comparison is possible and it's checked, the software is going to generate folders to store this data under the data folder. Then the user can define the subset, special extent, and the search period. That's only for the download of data, so it's not for the final plots. When you want to get the final comparison plots, you can redefine this special extent and the period also, which should be obviously within the bounds that you initially defined in the 5th step. Then the software is going to download, read, and convert the units of the data sets. It's going to subset them in smaller regions, and it's going to match the levels data if it exists. So we find sometimes that the data sets have total columns data, or they can also have partial columns data, or partial levels. I don't know exactly how to call it. But in this case, the first part of the problem is going to match this levels data. It's going to interpolate vertically, and it's going to find the nearest neighbor to in the CAMS model at the sensor grid. Then, and this is only for Tropomi, the averaging kernels can be applied. So this is in principle something that improves the CAMS model, and currently is having some errors that we have to check, but this is a functionality that is almost finished. Then it's possible to merge the total columns and calculate the difference. So you basically finally get a table with all the coordinates and the values in each of the data sets and the difference. Then, as I said before, the user can define, again, the plot spatial extent and period. And depending on this definition, the maps are going to show differently. And also, the user will be able to visualize the scatter plots that are adjusted to that spatial extent of that period. And yeah, finally, the user would get the final results, which I'm going to explain in the next slides. So for the main results, I made here a list, more or less, of what we can get after we match the data sets. So first of all, it's possible to visualize these data sets in maps and also observe the difference in different parts. It's also possible to get the merge table that I call, which is the place where you see all the values. And it's possible to get a descriptive statistics table with information about the mean and standard deviation of the variables or the position. Then I created a function only for, I created a function for to be able to retrieve a specific data for specific coordinates and get a time series to see how these component varies in different places or locations. Later, as I mentioned before, you can get maps by the bounding box that you defined at the last steps or by different times. You can also get scatter plots and histograms also by the bounding box and by country, season, or time. And finally, you can get these results aggregated or individually, so you can analyze a bit better the differences. Next slide, please. Thanks. So here I will show you a bit of which plots do we get. And the first one that we have here is the comparison between CAMS model and Dropomi sensor. This is level 2 data, so it's not very preprocessed. And actually, this data was kind of difficult to read and to subset because the data comes by scanline and ground pixels. It does not come by coordinates. Although it has auxiliary coordinates, it's not possible to retrieve these data by giving coordinates. So that made everything a bit hard. And yeah, well, here we can see an example for nitrogen dioxide over Czech Republic. And as you can see on the top, it's also possible to compare ozone data, sulfur dioxide data, and carbon monoxide data. Next, please. Okay, so here we have an example of monthly means. So here we are comparing the CAMS reanalysis monthly means data with the ASI level 3 data, which is already preprocessed and comes in a grid. So it's easier to compare and to handle. And we see that we can do this comparison for ozone and for carbon monoxide. For this case, specifically in September 2020 over Europe, we see that there are actually big differences between both data sets. And it would be interesting if someone could, I don't know, some researcher could check more months and see the differences. I will go back to this comparison later. Next slide, please. Then we can also compare the data from GOME2 level 3, which is also gridded, and is basically, we only have nitrogen dioxide in this case. We can see that there are some missing values for GOME in this specific map. I've used the data from method B, so I did not combine it with method A, but it's possible to do that. And yes, that's another example. We can go to the next slide. And then we have this other example. I would say this one was one of the hardest because we have, as you can see, a global data set that is level 2, so it's not very preprocessed. And we have data for different satellite tracks. And it's very important to match this data with CAMS by time. And that's actually something that gets complicated when you are initially handling ungridded data, and then you want to grid it, because in the moment you grid it, you change the coordinates, and the times, you have to kind of grab these times from the ungridded data set to the gridded data set. And so there is kind of a mismatch with the times. We have that for CAMS, we have the lead times I've got the lead times at 00, 6, 12, and 6 p.m. And for GOME, we have many other different times. So I'm actually matching the data by the nearest timestamp. And that can explain why we have some big differences in some areas of the differences plot. In this case, which is for ozone, and I combine the data from the 3 satellites, METOP A, METOP B, and METOP C. And yeah, it's possible to do this and also to visualize everything in different projections for nitrogen dioxide, ozone, and formaldehyde. Next slide, please. Here we can see an example of what I meant before by the retrieval of data by specific location. So this is for EASI. This is the data set I showed before. And it's for carbon monoxide, comparing it to the CAMS model. So we basically can input 2 coordinates or a list of coordinates, and we will get a table with the nearest latitude and longitude to those coordinates. And also we're going to get the value by each time. So at the end we can plot it and we can see some specific differences. Here we see, for instance, that in April there was a big peak of carbon monoxide. And I think that's quite interesting to see for different locations, to see if it's if this is happening or not, if spring is a bad month or is it not. Next slide, please. So here we can see the scatter plots I also talked about. So you can see we can actually plot in different colors each timestamp. So we can see more or less the variations. And we can get also data about the linear regression, such as the coefficient of determination or the intercept of the coefficient of equation. And we can also see the distribution of these values in histograms. Next slide. And here we can see a summary for winter, spring, summer, and autumn. So all the stations and all the seasons, sorry. And the thing with this is there is something here I didn't think about, which is that the seasons are not defined in the same way in all the parts of the globe. So I actually will have to correct this, because now this is actually realistic only for the north part. And it can be applied to Europe, but it cannot be applied to Australia, for instance. So that's something to work on in the future. Next slide, please. And we can also see the results by countries. For this, I have been using Google API, and we can see there are less points because I only used 1 month. And that can be interesting in case you want to analyze a specific country. But in case you don't want to, you can just use a bounding box to approach the study to a specific area. And that's going to be more simple, and you will not need to use any resource to make the reverse geocoding, which would be getting the name of the country by coordinates, because we're always working with coordinates. We are never working with countries' names. So that's something that I applied at the end of the project. Next slide, please. So here we can see 3 examples of the tables we can get about the linear regression. We can get these tables by time, and we can get them by season or by country, also by different bounding boxes. So that's also interesting to have as at the end to get some more details, some more detailed data. Next slide. Thank you. So just going into conclusions, I would like to say that about this package that I developed, there are still many things to improve. I would say that the first thing that matters now is to correct the application of the averaging kernels, because it can be something that is going to be used and is going to be pretty useful, I think. And apart from this, it would be interesting to include other data sets. And I was thinking lately that it would be also interesting to compare the satellite data to ground observations somehow. So that's something that's on the works for later. Since this is part of my master thesis, I will actually continue working on this until at least January next year. So yeah, I will see what's the direction, and I will commend this to my mentors, obviously. But yes, for now, the next data set that we're going to include is the ASCII level 2 data, which we parked now, but I can do this soon. And then I would also like to give some conclusions about this program itself. It has actually been very challenging sometimes because the data sets were not easy to handle, and because my background was not atmospheric sciences, it was actually a bit hard for me. But it was also very rewarding, and it actually oriented me in a work direction where I would like to continue being on. And I also would like to say that the support from my mentors has been definitely essential to understand and develop this project, as well as the resources that they gave to me, because without the server, for instance, I would not have been able to run the code fast enough. So these are things that I wanted to point out. Next slide, please. For the future work, as I mentioned, I would like to include more data sets. The next one is going to be ASCII level 2 data. Then I would like to correct applications of the averaging kernels. I'm interested on adding animations, because now it's possible to see the variations on time, but it's not in the same space. So I would like to be able to visualize this easily. Then finally, I would like to add a regridding function, which is going to help to compare the satellite data sets among themselves. And then if you have any other suggestion, I would also like to listen to it, and probably I would try to include it. Next slide, please. And that's it for my presentation. Thank you so much for your attention. If you have any question, you can write it in Slido, or you can just ask me at this moment. Thank you.
Thank you very much, Alba, for taking part in ESoC, for your great presentation and for your amazing results. So if someone wants to raise a question to Alba, could you go to a Slido and type your question there? Thank you.